right. Well, welcome everybody to Archive Dives with Oxen AI, where each week we dive into interesting research papers and try to tease out their key contributions so that we can apply them to our own work. This week, we'll be building off of a dive we did 2 weeks ago with Ben on specifically diffusion for text. So diffusion models have been pretty popular in the computer vision space. Recent models such as Sora show how you can apply diffusion plus transformers to generate some crazy high quality videos with state-of-the-art techniques. And so the question here is, can we apply some of these techniques that have worked really well for video and images, but apply them to text? And if so, what would be the benefits of doing this? And so we went over the paper a few weeks ago, but I think it's important to not only read the papers to stay on the bleeding edge, but also practically I learned the best by writing some code and running some experiments. So they had an open source repository for this paper that I took and kind of stripped down to its bare bones so that we could work our way back up and train a diffusion model for text end to end. We'll do it live today just on a character level, and we'll add like some print F statements and just like try to grok all the ins and outs of this model as we go along. So excited for that. And with that said, I will be sharing this Notion page so that you guys can follow along. And there's also a GitHub that you guys can dive into the code as well. All right, so practical dive, diffusion for text. This paper was called Discrete Diffusion Modeling by estimating the ratios of data distribution. And the archive paper is here. I took the code. Big shout out to Aaron, or it's either Lou Aaron or Aaron Lou, for writing the original implementation. If you guys want to follow along, this one is on the Oxen AI GitHub, and I've kind of stripped it down and made it work with character level so that we can kind of grok what's going on a little easier. But the high level idea is we're going to be taking noisy text, like this initial text in black here, and slowly diffusing it until it gets more and more coherent over time. So if you're familiar with diffusion for images, this is a very similar process. But the big contribution here is that the score entropy function makes it work for discrete data distributions rather than continuous ones like images. And we'll dive into why that's important and how that all works. If you want a deep dive on the actual paper itself, Ben did a great job last week. We've got all of his content on the blog and a separate YouTube video diving into the math of that paper, and Ben made it super approachable there. But before we dive into the code, I'd love to just even get a quick refresher on why would we do this at all. So the first interesting reason from the paper is that this score entropy discrete diffusion model outperforms GPT-2 on a model of the same size when evaluated with perplexity, which is just like how well can we predict the next word. And what's cool is not only can these models beat GPT-2, but as you diffuse them and as you increase the number of network evaluations, which we'll see how that works in a minute, the perplexity actually just continues to go down kind of as you diffuse over time. So the first time you generate the text, it still has a very competitive perplexity. You can see GPT-2 is kind of in the corner here. But as you take these time steps to denoise further and further and further, the complexity just drops and drops and drops, which is a pretty cool property to have. But GPT-2 is old. Some of you might be thinking that was like 2019 or so. So this is just kind of like a proof of concept that diffusion can work for text at all, and it's yet to be seen if we can scale these things up to like a GPT-3 or GPT-4 level. The other reason they quote for this being pretty important is that autoregressive models, like the GPT type, are not super optimized for parallel computation because you have the dependency of predicting the next word over time. So you have to predict the before you can do cat, before you can do sat, before you can do on, the, etc. And these diffusion models can take advantage of modern GPUs and just like diffuse the whole thing in parallel. So that's an advantage that the authors cite. And then the third one is if autoregressive models make mistakes, it tends to cascade. So Jan LeCun calls this generation drifts. And you can, think of if you were doing math, for example, and you wanted to do 25 times 25, if the network naively was able to multiply 4 or 2 by 2 at the start and predict the first token as 4, it's kind of screwed for the rest of the completion if the actual answer is 625. So hopefully these diffusion models can look at the entire context that it wants to generate and generate it all at once, as well as make it more coherent as you do the diffusion process.
Interesting fun fact is that LLMs do better on math problems if they output their answer in reverse, because then they're doing it from lower to higher digits. So I wonder if that would help
Yeah,
with something like this.
I remember you showing that or talking about that the other week. Is that just something you put in the prompt to tell it to do?
Yeah, you're like output the answer backwards. So for example, if it's got like decimals, then it's doing the decimals first so that it doesn't make mistakes like this as often, which I find like makes sense, but
Yeah,
it's not how we would do it.
that's hilarious. Funny hack. Um, so yeah, there's the errors cascading, and then I guess 3 wasn't the last one, but 4, this enables cool techniques like infilling. So let me get an example that Ben put together here. But you can actually prompt these models from any position. So you could do an infilling task where you want to fill in these 2 tokens here, and you kind of fix these tokens during the diffusion process, and then noisily just update the ones in the middle until you get a coherent sentence or like a more a better piece of text. And this could be interesting for like code completion, say, where you have like some context at the top and some context at the back, and you want to fill in the middle. So we'll see how that works as well today. So diving on into the code, GPT-2 was trained on an unreleased data set. They called it open web text. I went and grabbed a reproduction of this data set and put it on Oxen AI to run some of these experiments with. If you're not familiar with Oxen AI, we store large machine learning data sets, version them, and allow you to collaborate on them. So for instance, this is like a 24 gigabyte repository of text with a bunch of Parquet files of this giant web crawl. So you can see each one of the shards has like 100,000 rows in here. And this would be an example of a pre-training data set for some of these LLMs. And the models that they were working with in this paper were trained on a similar corpus, and they were trained with the same model sizes as GPT-2 and also have the same tokenizer as GPT-2, which has 50,256 tokens, which we'll see is pretty important here as we go along and just like keep these sizes in our head. I stripped it down to also work with a character level tokenizer so that we can actually see what's going in and out a little easier. But this number will be important to keep in mind as we go along.
How long did it take you to upload OpenWebText to Oxen?
It took like 200 seconds. So I did that all in AWS, but like one of the big benefits is the speed of Oxen. It just
Yeah,
blazes through uploads and downloads.
that's awesome.
So when working with these models, I love to just start with the pre-trained ones, and they released some of their pre-trained models. I also put them on Oxen for you to download if you want. Basically, these models are just grab this to show you. They're just PyTorch models. So this repository is just the checkpoint here. They're relatively small, so 1.7 gigabytes, and they come with a config file for all of the model parameters. So this is similar to like a GPT-2 large model configuration where the hidden size is 1024. The context length is also 1024, and then they have 24 attention blocks and 16 heads within the attention block. And all of the other parameters you need for training are also in that config file. So diving over to VS Code, I have all of the code for all of this here and on that GitHub that I linked at the top. So I wanted to start by just sampling from the pre-trained model. So a few things to keep in mind with this code base is to start, we'll be using the GPT-2 tokenizer. Basically, you can load this SEDD model, score entropy discrete diffusion model from the checkpoint. There's going to be this important component called the absorbing graph. And then there's going to be an important component called noise, which is a log linear just noise function that we can sample from. And then we have a sampler that will actually run the diffusion process given the tokenizer, the model, the graph, and the noise, and some intermediate steps, or the number of steps that you want to run. So let's start by just running it on one step and make sure our Python paths are good to go. And make sure that we are pointing it to the right model directory as well. So we can see the vocab size is 50,257, which is an interesting point to note. If you look at this, they actually add one, what they call like an absorbing token at the end, which is basically just an empty string. And so that's why we get a 257, and we'll see why that's useful here in a second. But this first generation of text is pretty noisy and has some like Unicode issues, and definitely not like the high quality text that we're used to getting from a language model. So basically what we can do here is increase the number of steps for diffusion to say 128. And what it'll do is it'll start from this really noisy text. We will sample over time, and eventually we get something that's much cleaner. So this looks a lot more coherent, even just from the first glance at it. None of those Unicode errors or anything like that. And but when you dive in and read it, it's still a little incoherent. So how guess the undrafted scorer wears 54? Wouldn't say like that's the most coherent text, but definitely looks better than the start. And if you remember that graph from before, you can crank this all the way up to like 248 network evaluations or diffusion passes, and it'll just get more coherent and more coherent over time. So the first thing I did was peek under the hood of what's actually happening during this diffusion process. So I have a little variable in here called show intermediate. And this is going to start to print out the intermediate representations as we're diffusing over time, just to give us a better sense of what's going on here. So the first thing we can see is that we start at time step 1, and depending on how many steps you give it, basically we take like just a linear map of 0.1 to 0.9 to 0.8 to 0.7, and we're going to be feeding this time step into the model so it has a little context of how noisy is this text at this particular point in time. And the second thing you should notice is I'm printing out all of the token indices here. And the model starts out by predicting a lot of 50 to 57. So if you remember, that's like our vocab size here. And the last token within our vocabulary is actually just an empty token here. So I'm not only printing out the indices of the tokens, but the decoded sequence here. And you can see this decoded sequence looks a lot shorter than our like full context window of 1024 because it has a lot of these blanks within there. So initially, when we tell it to sample at a noise of 1.0, it gives you like this short sequence, and then it slowly starts flipping some of these blank tokens into actual tokens in the sequence. So you can see it starts with we sound, and then at time step 2, it finally flips this to I never we, and then I never we, and then I never comma, and it slowly gets a little more coherent and a little more coherent over time, starting by flipping that last token in the sequence. And I only ran it for 10 steps here, so it's still relatively noisy, but keep kind of those numbers of the time steps and the tokens that are actually coming out in mind as we go along here. So the next thing to point out is what is this noise and what is this kind of graph that we're using within the code here. So if you came to Ben's talk last week, you'll remember he mentioned the fact that one of the reasons that diffusion is really hard for text is that text is discrete variables instead of continuous variables. So what that means is, each one of these indices are a discrete value here, and it's really hard to transition between a token. Like if you transitioned from token 25 to 26, that could completely mess up the meaning of the sequence. So what they do here is they have this kind of transition graph, and they have this nice diagram in one of their blog posts of transitioning from a Hamming distance of 1. So Hamming distance is just like how many flips within the sentence did we do. So in this case, we just flipped the first token. In this case, we flipped happy to sad. In this case, we flipped 2 to that. And what this absorbing graph does is take care of the flipping process of just one token to another.
Wait, in this example, are happy and sad like adjacent token numbers?
No, so they could be anywhere within the vocabulary.
So you're doing it not by 25 to 26, but by meaning.
Yes, that's the idea, is hopefully it can look at the whole vocabulary size and say, given this position in the sentence and all the context around, flip to a more likely token in that slot. And so I have a little demo script of what just this flipping process looks like.
Okay.
Yeah, do we have another question?
Just a quick question on this. So on that string that you showed, do they go by the position, or do they just randomly choose one of the positions and flip it? That means I could do the first one, that is I, or do I just take randomly, or do they do a random number? They pick a random position and then flip that.
Yeah, so they do all the flipping in one pass, and we'll kind of see this as we go along. But each time you diffuse, you could potentially flip all of the tokens or a subset of them. And then for each token, you have a probability distribution of what is the best flip we should make given our vocabulary and given the whole context. Does that make sense?
Yeah.
Cool. So I have this little script to kind of demo the perturbation. So if we look at it, I load in our tokenizer, I tokenize the sentence, I pass in a time step that we want to noise by. I load our absorbing graph, our log linear noise, and basically they have this sample transition function from the graph. And this is what's going to perturb our tokens during the training process. So I passed in applying diffusion to text is kind of crazy, and then a time step of 0.35. And so we have this text, which leads to these tokens. We pass in the noise of 0.35 that runs it through this log linear function. And then eventually we get spit out some shifted tokens. And the shifted tokens always shifts to that last token there. So the shifted text looks like app to is kind of crazy. Although it looks like it's dropping these tokens, it's really just flipping it to that last index here. And you can see that 52, 57 here, here, and here. And so during the training process, what they do is they have this loss function here. And for every batch that we get in, we take in the model, the noise, and the graph. We basically get some noise given a time step, and this time step is just a random number between 0 and 1 with an epsilon of like a certain value. So it might be like a random, depending on this epsilon, you could be taking smaller time steps or larger time steps. But basically they call this graph sample transition function that perturbs that whole batch, runs it through the model, and then computes some sort of loss based off of the perturbed batch and the correct batch that comes through. So if we look at this sample transition function, it is pretty straightforward. So they take in the noise, and let's actually like print out some of these values to see what they are. So they take in the noise, they predict some move indices, they perturb all of those indices, and then they return the perturbed sample. So if we look at what that all looks like together, you can see that they compute this move chance. And remember, it's log linear noise. So that's why they take the exponent here to reverse the log. And now you get out a move indice array here. And this is a batch size 1, but you could imagine, batch size n with a bunch of different examples. But it's basically saying, okay, what's the chance we want to move? And that chance is 0.34. And then for each token within the sequence, okay, we want to flip this one. We don't want to flip these two. We want to flip this one. We don't want to flip these ones. And so it's basically just like saying, is a random number lower than the move chance? And if so, we're going to flip that one to the last dimension, the last token ID in the sequence. So if we cranked, yeah.
Sorry, there's a question in the chat. If you could give a little more intuition on like the graph and how to think about that and what its role is and all this.
Yeah, so we're looking at the graph right now. And this is a component of it, of how we know like which tokens to flip. So in this case, if we pass in a very high value here, the move chance is going to be really high, 0.99, which means we're flipping all of these tokens. If we pass in something really low, the move chance is going to be much smaller, and we just flip these tokens here. So you can see like all of these changed. Does that answer the question, or is there a follow-up?
Nothing yet. Makes sense to me.
I have a question. So these flips happen during the diffusion steps, right?
Right now, we're looking at the training process. So during training, basically, we'll be sampling a random noise value. We'll be perturbing the batch. We'll be running the perturbed batch through the model, and then we'll be comparing the perturbed batch to the ground truth to compute some sort of loss. And that's kind of how they progressively train the model, and then we'll show how we use that for sampling next. Cool. So that's the training process. Hopefully you can kind of see as we put in a low T, it only flips a few things. As we put in a high T, it flips a lot of things. So then if we go to our sampler, which is in here, basically what we do when we sample is we generate a bunch of time steps depending on how many we want to diffuse. So in this case, like if you put in 128, it would generate a list of time steps from 1.0 all the way down to 0. And we basically iterate over those steps. We predict a new X out at that time step. We decode it, and that's kind of exactly what I was showing on this flag with show intermediate, is at each time step, we start with how much noise are we at, run it through the model to get a new X out, and the model's job is going to be, given the current sequence and given the time step, tell me which one of these to flip. So I'll pause there for any questions about like the general training process versus the inference process.
Just a quick question on typical vision transformer. If you see, there is a forward pass and a backward pass. Remember that the one that you take a normal image and then you diffuse or add noise to get to a very noisy thing, and then you reverse it. So in this case, how do you kind of what would be the analogy here? What would be the forward pass here? Is there something of that sort, or are you just kind of taking in the training step a given string of text, and then you're kind of just adding noise by choosing this time period and flipping? That's the kind of that would be the forward process here.
Yeah, so the forward process is each one of these time steps is one forward pass, and the inputs are like the current batch and a time step. So really, in this case, we ran 10 forward passes to do the denoising. And then during training, the backwards pass is you take this loss function that's perturbing. You take the perturbed batch, you take the regular batch, you compute this loss, and then you're going to do a backwards pass from this loss to the model parameters to know, given that time step and given the perturbed batch, try to predict which tokens we flipped and which ones to flip them to. Does that make sense? Cool.
Okay. One more question on that, spurred on by something in the chat that I thought was really good. I haven't had a question of, does anyone know how we choose the new token to swap to? And just like, there was a little bit of discussion about that probability space. I know that in the blog post that we went over last week, they kind of implied suggestively that it could be, yeah, you just pick any random token. You were talking here about trying to find tokens that are closer together in embedding space or just in semantic meaning to the sentence. anything you can shed light on there?
Yeah. Did you have any part of the blog that you wanted to like link to?
I guess
Or
just like, so it's not just a fully random swap one for anything, correct?
correct. Yep.
Okay.
So let's actually look at demo loss for this, and I think this might shed some light. So let's look at the score function, and let's look at what comes out of the score entropy here. So I'm just going to pass in oxen plowing fields of gold as the text, and then 0.05 as the timestamp. And then we're going to compute loss for this particular example. So this is still the move chance, the move indices, and we perturb that initial sequence of these tokens given this move chance. So now we have a perturbed sample here where this indice, this indice, this indice, these are all flipped. And we know this because we did the flipping ourselves. And basically what comes out of your model is what they're calling the log score here. So you can see its sequence length by vocabulary size. So for each token within the sequence, we get this log probability, that probability distribution that comes out. And that's supposed to capture, okay, at this sequence or at this index in the sequence, how probable are we to flip to some other token? And we know this at training time because we like sampled a real value from the distribution. And then basically for the loss, we can zero out the ones that we didn't flip and say how well did that prediction map to the real value there, the real Y.
Got it. Okay, cool. That helps a ton. Kaiser in the chat also nailed it, which I was not fully sure, but now I am. So that lines up really well. Thanks.
Okay, nice. Cool. So that's kind of the guts of everything here. And I thought it would be fun to run an actual train on one of these models and just like kind of watch it go. Oh, I guess the last thing that would be really cool to demo before we do an actual train is the infilling capability. So there's also a script in here where you can run a conditional sampling. And basically what this is going to do is take in a prefix and a suffix. We're going to tokenize them. We're going to get the prefix and suffix IDs. So it might be something like this. We're going to get the locations in the sentence, and then we're going to fix the values there as we're doing the diffusion process to always be those indices, so we can never actually flip those values as we go along. And so let's do hi, my name is as the prefix, and that's why I'm late as the suffix, and kind of watch what happens here. So we're doing this for 128 steps again. This is pretty easy to run on a relatively commodity GPU because the model's not super big. But you can see that the diffuse text here started with hi, my name is, and it picked Don. And then thanks for the help provided in the comments, blah, blah, blah. Something about Ethereum and address. And then at the end of the sequence, it says, and that's why I'm late. One thing that I was thinking as running through this example, because it's one of the things that they really call out as a benefit of this approach, is being able to infill anywhere. That's true, but it also depends on the context size that you give it. So in this case, if I just wanted to predict like 2 words in the middle, In fact, if I wanted to predict anything in the middle, usually with text, you don't know how big that sequence is going to be. So it seems like kind of an odd benefit to me of being able to infill if you have to fill in the whole context there. So I was thinking potentially you could change the training regimen to add those like empty strings in between and only predict and then predict like a variable width in the middle. But they didn't do that in this training regimen. They just concatenated all the text and always filled the entire context window of 1024. But something practically to think about when you see that diagram of like infilling, and that sounds great in theory, but in practice, there would need to be some tweaks to make that, I think, work really well. All right, cool. So with that said, I did a nice little training script here. And I did a few different experiments. I'll see which one is loaded right now. The baby names data set. Okay, that's going to be a fun one. So what I did was I swapped out the tokenizer to just a tokenizer that does like character level, which is pretty easy to do. There's just an ABC tokenizer in here. So I took all of the characters to be like ASCII characters, digits, punctuations, a new line, and a space. And then it just has like a pad and an unknown token. So this vocab is much smaller than our 50,000 GPT-2.1, but it'll also make it a lot quicker to train. And then I grabbed this baby names data set from Oxen. So we're just gonna like predict baby names. So there's this, from the census, like Emily, Hannah, Madison, these are all the top names here. And I split them into like a train and a test set. So we have some wide variety of names that we're going to try to predict here. Definitely not sorted by relevance because these are some names that I've never seen before. But it'll be a good, just like quick demo of how this training process works. So punctuation. You can kick off a train, and then I'm going to be saving the results to an Oxen repository as we go along here. And so not a very large model here. Let's see, this is going to spit out all the print statements that we had before. So let's get rid of that. Within the loss function, and then also within the graph here. Okay, so we're preparing the data set, tokenizing it, and then we kick off. And so it just did the first evaluation on the validation set, and I put this in SEDD baby names, I believe. Yep. And so after the first 1,000 steps, we're going to do a sampling and see what the model has learned. But you'll see the loss slowly dropping at the start here. Went from e to the 2 to e to the 1. We just predicted some outputs, and let's see. I thought I put that in this repo. Said baby names. That's live demos for you. Here we go. sample.txt. Okay, so first pass, not anything super coherent, but we did have a context length of 32, and you can see it's already learned like to put all of those spaces at the end and just predict some sort of text here. And we'll see as it goes along. It just did another sampling, and I'm saving all of these versions out as it samples at each step. And we can see, okay, the next step, still not super coherent yet, but if we run this for longer and longer, eventually we'll get baby names out. So feel free to play with this code on your own, try it with the full vocab size, try it with a small vocab size, but it is up and running and it is working, and it's also tied to this little eval, so we can watch like the loss drop as we go along. So pretty simple telemetry in there, but it's working, and I hope that kind of gives you a sense of what these diffusion models can do, what these diffusion models cannot do, and my last kind of takeaway of this whole thing, or I guess I have a few takeaways, are that it's cool in theory. I'm not yet convinced that this is the right path for text. Still some research to be done, like scaling these things up to actual GPT size. The infailing capabilities wasn't a huge selling point for me with like the actual implementation that we have today. I could see how you could extend that to be a little more useful. But I think diffusion should not be used for text, at least yet. And I'll pause there for any questions or thoughts. Please change my mind if you have other opinions here.
Either or question. I can see where you can couple diffusion with a regular transformer decoder model.
Yeah, I don't think it has to be either or. You want to talk a little bit about how you would see those interacting?
Yeah, I mean, it could just be used as the diffusion model can be used as like a keyword input to the decoder model, to increase accuracy is one idea. There's other ways it can be used, yeah.
Yeah, totally. Or I could see it kind of as like a editing step.
Yeah.
Before or after, where like Ben and I were talking about this before, where we totally, as humans, speak and write left to right or right to left, depending on what language, and like, but then we go back over and edit it. So maybe some combination of the auto-regressive prediction and then the diffusion to make it really good could be a nice user experience.
Yeah,
like
yeah, for generating like large books, diffusion would be very, much better than just standard decoder, because it could generate stuff for each chapter right away, and then the decoder could fill it in.
Yeah, totally. The one thing I would call out there is you still have like the context length restriction, and even that matrix we saw of the output of like vocab size by context length, that's going to take up a lot of memory even for the diffusion models. So something to think about scaling.
A few years down the road.
Yeah, totally.
I
Cool.
think it's interesting, and we talked about this last week after as well. Someone had the idea of like kind of generating a basically, this is all heuristic, but generating an outline type of thing with a diffusion model that can fit in context, that kind of conveys the vague idea, and then kind of using LLMs, or sorry, using like autoregressive LLMs to super resolve that from the various chunks of the outline. Obviously just like, kind of making stuff up here, but seems interesting in theory.
Yeah, he talked about that in terms of music generation, right?
Yep.
Yeah, like you know more about music than me, Ben, but generating the high level features of the song and then like filling in the details there.
Yep.
Yeah. Cool. Well, I'll kill the recording here just in case somebody wants to hop on and not be on the YouTube, but thanks for watching if you're on YouTube, and thanks for joining live, everyone. This is a fun one.